Okay, so the topic is going to be the diversified treatment under ambiguity. The application to tuberculosis, I mean, this is a full-scale paper, but I'm going to use it as an illustration of a methodological theme rather than getting deeply into the TB issue when we get to that. But before we get to that at all, here is my, right here, here's my apology to my colleagues in econometrics or in economic theory who had to suffer yesterday through an entire hour of lecture without any math. And I think I push them as far as I can in listening to English without any math. So, but I know the rest of you, or some of you who don't want math, well, just give me about 5 minutes with this to put up a little bit of math to lay groundwork. This is going to, it's not hard at all, but it's a bit abstract. But it's going to be used in the work on diversified treatment in a much lighter way. But I want to, for those of you who are not familiar with basic decision theory, and I mentioned criteria like max-min and minimax regret, just to see them in abstraction as to what they are. Just want to do that. It's a few slides, and then we'll go on to the main topic. So there wasn't time to do this yesterday, but we have more time today. So the starting point for decision theory, it can be applied to public policy or to anything else, is to say that the planner or the other decision maker has a predetermined choice set, capital C, and believes that the true state of nature, which we might call S star, lies in some state space. State space, you remember from yesterday, is all the possibilities that you think may occur. And then you have a welfare function, it's a social welfare function, that's called a W, and it maps action and states of nature into the real line, into a welfare value. So if I tell you a particular action and I tell you a particular state of nature that may occur, then I get the welfare that goes with that. Now, what the planner would want to do, it's very simple, is to maximize, and put it up on the laser pointer here, is to maximize, if you knew the true state of nature, S star, then you would want to maximize welfare over the choice set. The problem is you don't know S star. Okay, so you can't, that's why you can't solve the maximization problem. So this is where the whole issue is. And as I said yesterday, the state state provides the basic decision theoretic expression of uncertainty, and things that are not in the state of nature are presumed to be impossible to occur. And what's in the state space is like everything you don't know, either about the physical environment, the social, economic environment, and also everything you don't know about the welfare function directly. So I mentioned this yesterday with utilitarian welfare function. You have to know the preferences of the population to know the welfare function. So if you don't know the preferences of the population, then that's in the state space too. Okay? Now, the state space is subjective. It's your starting point, and you're primitive. And even though it's subjective, it doesn't mean it's arbitrary. In fact, the whole point of scientific research, whether it's econometric research or physical science research or any research from the perspective of the planning problem, is to try to learn about what could possibly happen in the world. Right? Learn about the physical, social environment, learn about people's preferences and so on to get as small a state space as possible. That's why we do our research, is to be able to shrink the state space so we know more and can make a better decision. And we do that by combining plausible theory with careful empirical analysis. This is the kind of what's in our minds when we do research and when we teach this material. Now, okay, so you have a state space, you use whatever information you have, and now we have to make a decision. Now, in decision theory, it's long been viewed as a two-stage problem. The first stage is very simple. I will talk it through, and the math is right here on the slide. The second stage is where all the difficulties are. The first stage is to eliminate actions that are dominated. Okay, so to say it in words, we don't know the true state of nature. But let's say two possible actions, call it actions small c and small d. And if I were to know that regardless of what the truth is, regardless of the true state of nature, that action D yields at least as good an outcome, and welfare outcome, as action C. And in some possible state of nature, action D is strictly better than action C, then clearly action C should not be chosen, right? Even though I have uncertainty, if I know that D is better than, weakly better than C in every state of nature, and strictly better than C in some state of nature, you should throw out C. So the first stage of decision theoretic analysis is to eliminate dominated actions. A bit easier said than done. It's conceptually, it's just what I said. There's no more to it. In a particular analytical context, it may be hard to determine which actions are actually dominated. And so sometimes this step is skipped, and you go immediately to the second stage, which is choosing among the undominated actions. But you should try to eliminate the dominated actions first. I'm going to discuss this here in a context without sample data. I have on the bottom here, I say that Wald, that's Abraham Wald, extended the theory to settings where the planner observes sample data. This is an area in which I've been working myself, on technical analysis quite heavily, almost for 20 years, extending all this to use of sample data. I first published on this in 2004 in Econometrica, and there's a long string of papers on this now. But we don't have the time to get into this, so we're not going to do anything about the extension to having sample data today. Okay, now the problem is if you've gotten rid of the dominated actions and then you have the undominated ones, all of the issues of the undominated ones, what that means is that maybe action C is better than D in one state of nature, but D is better than C in another state of nature. And I talked about that yesterday, and that means you just can't say definitively that C is better than D or D is better than C, because there exists a possible real world in which it could go either way. So then the question is, how are we going to make decisions? All the controversies in decision theory about trying to get a reasonable procedure for making decisions is about how you're going to behave in these undominated actions. So I'm going to list three criteria, two on the slide and one on the next. The one that's most familiar to economists is to say, well, they have this state space, capital S, all the possibilities, put a probability distribution on it. Maybe an objective distribution that you know is correct. Then we in economics say that the person has rational expectations. That's what rational expectations means. If you actually know there is a real world probability distribution and you know what it is, then you have rational expectations. Or it could be just a subjective distribution in your head. In Bayesian analysis, it's cognitively, psychologically well-defined, but it may not be related to the real world. And then what you say is, well, I'm going to maximize subjective average welfare over the choice set. So here's your math, is that for any given action C, we can form the expectation of W, hold C fixed, and then take the distribution over the state space S, and this is your expected utility or expected welfare, and then you choose the action that maximizes expected utility or expected welfare. That's all there is to it. Okay. The great preponderance of applied work in economics, when it faces up to uncertainty at all, it does it this way. But I mentioned yesterday, and we're going to be much more forceful on it today, that my own work is focused on cases in which you don't feel capable of putting a probability distribution on the state space. It's just, it doesn't come free. It's adding a lot of knowledge to say I can put a probability distribution on the set of possibilities, and you may feel uncomfortable doing that, okay? And just not feel like you have a credible basis for asserting the probability distribution. So then you want to have some criteria for choosing an action without a probability distribution. The most classical one is the Maximin criterion, which says, well, I can't put a distribution across the possibilities, so let's look across all possibilities and ask, what's the worst thing that could happen to me if I choose any given action? That's this right here. if I take any particular action C, then the worst thing that could happen to me is I'm going to get the minimum welfare across all states of nature. Well, that's a bad thing, is to get the worst possible outcome. So let's get the least bad worst thing. So you take the max here. This is maximin. Okay? Maximin if you're trying to maximize welfare, or minimax if you're trying to minimize loss. It's just one's the negative of the other. It's the same thing. This goes back, I think in the modern literature, to at least to von Neumann in 1925 in Theory of Competitive Games. I don't, it may go back earlier, but that's a place, it goes back 100 years. The issue with maximin always has been, it's obvious just from the statement of it, is that it's conservative. It's you're just being very pessimistic. What's the worst thing that could happen to me, and I want to get the least bad thing. Now, you can't say that it's irrational to do that. It's perfectly coherent and well-defined, and you may want to be pessimistic in that sense. But, a lot of people tend to think it's like too conservative, if you will. The other possibility in the literature, and this is the one in which my own work is focused, is called minimax regret. And the math is slightly harder to parse, but it's right up there on equation 3. Let me talk it through, and then we'll see each one. What minimax, to start off with, what we want to do kind of a worst case analysis, but very different than a maximin. What we're going to do is we're going to start by imagining any particular action and then any particular state of nature and ask what's actually the best thing that could happen in that situation. So if I imagine the best thing, the best choice I could make in that state of nature, well, that would be this inside here. Is that if I knew that the state of nature is S, then I would obviously choose the action that maximizes welfare in that state of nature. Now, if we knew how to solve that problem, we wouldn't have any uncertainty, but we don't know what S is, so we can't actually solve this, but we can certainly hypothetically ask, what is that maximum? And then we compare that, this is the subtraction, is we compare that with the welfare we'll get with any action C, which may not be the optimal one, so C may be suboptimal. The difference between the best that could happen in this state of nature and what we might actually do with action C, that's called regret. And regret, it's a kind of a nice term because it really does bring to mind psychological regret. Because if you think psychologically about regret, you would say, I made some choice, and then I find out afterwards I could have done better. And then I feel regret because I didn't make the best possible choice. And so my regret is the difference between how well I did with the choice I made and the best I could have done. Well, that's mathematically exactly what this is saying. Well, that's regret. And the word regret is fine. I rather abstractly think about it as the loss relative to the optimal, is how far you are from optimal, okay? So you don't use the psychological term. Now, the problem, of course, is we don't know the true state of nature. So you'd like to minimize regret, clearly, but you don't know the true state of nature, so you can't do that. So then you take this maximum here across all states of nature, that's maximum regret, and say, and so now instead of looking ex post, as a psychologist would, at my regret after making a decision, I look at it ex ante before making a decision, look at all the possible states of nature that could occur, and ask what's the maximum loss relative to the optimum. That's this maximum regret over here. And that's bad, so you'd like to minimize that maximum regret, and then you get this minimum over here, okay? So this is mathematically the definition of minimax regret. And it is, as I said, maximum regret is maximum distance from optimality, and so it's uniform nearness to optimality. That's maximum regret. This comes into the literature in words, not in formality, by Leonard Savage, the same Savage who did axiomatic decision theory that I mentioned yesterday, in 1951. And it's been in the literature ever since. And that's a different criterion, one that I found very congenial. It has for the people who like axioms, it's been somewhat controversial because it doesn't adhere to an axiom that some decision theorists think important, called independence of relevant alternatives. Some of my faculty colleagues here have asked me about that over the past day. We've had some discussions. I don't have the time to really go into it here. Just want to mention that. But maybe in the Q&A time we could go into that further. Well, that's about it for this abstract math to go, as background. What I want to do now is forward to the topic where we're going to actually use this in a pretty simple context, but I really want to, focus on the applied context, and we'll see how this plays out there. So the topic is diversified treatment under ambiguity. This has been developed through a whole series of papers. First in a chapter in a textbook I wrote in 2007. And by the way, for students, I think both for any PhD student, but also for an upper-level undergraduate, this book, IPD, means Identification for Prediction and Decision, Harvard University Press, 2007. This is this is a textbook that I use teaching first-year PhD students in econometrics. I've used it in upper-level undergraduate classes at Northwestern as well, and I think it's pretty readable, and it is much more of of course it's mathematical, it has to be rigorous, but it's really much more focused on the concepts than on the technicalities. So I think you can learn a lot from it, I hope. So it started there. Then I wrote a full journal article in 2009 in the International Economic Review. That's the paper I'm really talking from right now. The tuberculosis work is an applied paper that was done 10 years later with Rachel Cassidy, who's English, and she's now at the World Bank. She was actually an Oxford PhD and then did a postdoc at IFS, and I got to know her there. And now she's at the World Bank. She's a development economist, so I'll say more about that when I get to it. Now, the context that I want to talk about, so you'll see this is a very real-world application, is the very widespread problem of program evaluation and treatment choice. So we have a vast amount of work in economics, in medicine, in education, in many, many areas where you think about having some treatments available that a social planner could administer to a population. And you could do it at a micro level. This is not a macroeconomic problem where you have to make one treatment choice for the whole population. It's not like choosing national defense, where you can't have separate national defense for each person. It has to be just one national defense for the whole population. I'm talking about the kind of micro level treatment choice, like in clinical medicine, as I talked about yesterday, or in educational decisions for children and active labor market programs and so on. And you have some treatments, and you want to choose the best treatment possible. Well, if for those of you who have any familiarity with the literature on analyzing treatment response or treatment effects, very, very common notion is that what you want to look at is the mean outcome in the population with given treatment allocation. There's a group of people here. I could allocate to each one of you some treatment. I'm just going to talk about in a very simple case where there are two treatments, treatment A and B, but there could be more. And I could, each of you could get a treatment, and then we could see your mean outcome, and I'd want to maximize the mean outcome. So that's clearly what's going to happen in a utilitarian context, where the mean outcome would be the mean personal welfare outcome. And what you really want to learn then is the average treatment effect. On average, is treatment B better or worse than treatment A? And if it's better, then give everyone treatment B. If it's worse, then give treatment A. Everyone treatment A. Now, doing that, saying I could maximize social welfare by choosing an optimal treatment presumes that I actually know average treatment effects. And so that now it doesn't actually require that you know the exact value of average treatment effect, but you certainly need to know the sign of average treatment effect. On average, is treatment B better than treatment A or worse than treatment A, okay? And then you'll be able to optimize. Where ambiguity is going to come in, and this is going to be very, very common, is that you may not be able to get the sign of the average treatment effect. Okay? You may be able to learn something about the average treatment effect, but not enough to know whether on average treatment B is better or worse than treatment A. Why might that happen? There are so many reasons. Let's start with the case where everything is wonderful and you presumably do know the sign of the average treatment effect. The kind of classical case where it's realistic to assume that you do know it is if you were able to run a classical randomized experiment on the population. And let's not worry about small sample size. It was a big sample, so we don't have statistical imprecision. And there were no problems with the experiment. So for anyone who studied randomized experiments or randomized trials, then it means you draw people at random from a population. There's no problem getting informed consent for people to participate in the experiment. And then everyone gets the treatment they're assigned. There's no compliance problem, which is a major issue in practice, that people don't actually take the treatments they're assigned. And then you will actually observe the outcomes that occur to them. There's no missing data in the outcomes, and so on and so forth. And then you can actually learn the average treatment effect. And good. Well, a lot of the literature assumes you have that kind of data. But in the real world, that's actually very rare. If we stick to randomized experiments, then everything I said, all the things I said that I'm assuming happen may not happen. It may be that you can't randomize the entire population. You have to get informed consent for people to participate, and you may have systematic selection into who's willing to participate in your experiment or not. And then if the people who participate in the experiment are different than the ones who don't, then we have systematic selection. Selection bias is the colloquial word. And we may not be able to learn the sign of the average treatment effects. Or it may be that people do sign up for the experiment, but once they see whether they're randomized into treatment A or treatment B, they say, I was randomized into A, but I really prefer B, so they don't comply. Okay, that's a big problem in the real world. Or they drop out of the experiment after they've begun. They attrit from they just leave the experiment and you never observe their outcomes. All of those issues, selection into participation in the experiment, non-compliance, missing data from attrition, they all generate identification problems. Now, you can make assumptions that are strong enough to deal with those, but those assumptions pretty commonly will have incredible certitude. And so if you attack the problem the way I would, with weak assumptions, then you will get bounds on average treatment effects. Okay, and all of this is laid out formally in this textbook that I mentioned on identification for prediction and decision, and in many, many other places. You will get bounds on average treatment effects, and the very common situation is that those bounds are going to cover zero. So you won't be able to get the sign of the average treatment effect. Then you will be in a situation of planning under ambiguity. Okay. Then the question is going to be, given that you don't know whether treatment A is better or worse than treatment B, how are we going to proceed? Now, the literature has typically, in terms of the theme I want to develop here, the literature has typically presumed that whatever you're going to do, you're going to give everyone the same treatment. And what I mean by everyone, I should say, make a singleton allocation assigning all observationally identical persons to the same treatment. Let me say, where observationally identical means that people may be heterogeneous. They may have different covariates. There may be men and women, and there may be people of different races, people of different educational backgrounds, different health status, if it's a medical context. To the extent that you can observe those covariates, you can stratify the population according to those groups. So let's say you've done that. You've separated people into different groups. But once you've used all the information that you have about people, then they're going to be observationally identical within those groups. Okay? So that's what I mean. So I don't mean that you have to necessarily give everyone the same treatment, but I mean that you give all white males who are age 41 and who have a certain health history the same treatment. That's what I mean by a singleton allocation. That's the typical way the literature proceeds. However, what I realized back 15 years or so ago is that you don't have to do it that way. You don't have to give everyone the same treatment, within each group. You could do what I call here a fractional allocation. I could give 30% of people treatment A and 70% treatment B, okay? Or I could give 60% and 40%. If I'm the social planner, and if I have the power to do that, and I want to come back later to whether I actually have the power to do that, then I could give some fraction one treatment, some fraction another treatment. If I do that, they're going to be randomly allocated because these are observationally identical people, so it's necessarily going to be a random allocation. Now and what I'm going to think about here is having these fractional allocations. Now, this notion of a fractional allocation, which I think it's a contribution for my work, it was not in the literature. It may remind you of something. It may remind you of a portfolio allocation in finance, because doing a fractional allocation is exactly diversification in portfolio allocation in finance, okay? And it's not just a metaphor, it's actually formally the same thing. If you think about the classical portfolio problem in finance, where let's say you have two treatments, stocks and bonds, okay? I'm an investor, and I've got 1,000 British pounds, and I could take each, let's say the 1 pound is the smallest denomination that I can allocate on the market, and I could put all of my 1,000 pounds into stocks or all of it into bonds. But I don't have to do that, of course. I could put 600 pounds into stocks and 400 into bonds, and so on. That's classical diversification. In finance, diversification is a very, very important concept. Why is diversification an important concept in finance? It's because of uncertainty. If you knew the returns to stocks and bonds, then there'd be no reason to diversify. You would just take the asset with a higher return, and you would put all of your money into that asset. The entire rationale for diversification in finance is because of uncertainty. Now, for those of you who have had any classes at all in finance or in economics, then you say, well, what's the theory that leads to diversification? It assumes maximization of expected utility. That's the first criterion that I used on the previous slides. And as everyone knows who study this, then utility is a function of money, return. And if you're risk neutral, so if utility function, your W that I had before, is linear in money, then you do not diversify. But if your utility function is concave in money, then you're what's called risk averse. And if it's sufficiently risk averse, and if the spread of returns is large enough, then you do the math, and the optimal thing to do under that expected utility maximization is to diversify, okay? Now, what I'm talking about is exactly the same, except I'm not diversifying British pounds, not 1,000 pounds, and I put so many pounds in stocks and so many in bonds. I'm going to have a population of people rather than banknotes, and I'm going to put some fraction of people in treatment A and some fraction in treatment B. How would you then justify diversification of people rather than banknotes? You can do it the same way with expected welfare maximization that I had on the earlier slide. You could say that my social welfare function is a concave function of some outcome of interest. It's like a money outcome, or it could even be people's income. It could be just concave function of income. And then I might wind up diversifying people in exactly the same way as in finance theory, okay? Now, I could have just said that, and we'd be done in terms of actually doing methodological work. But of course, what I was interested in was dealing with this problem when you don't have a probability distribution. And so when there's no probability distribution, then you can't maximize expected utility anymore. So what are the possibilities? You could use maximin or minimax regret. And then you can just crank out the very simple math of this problem. And that's what I'm going to go through quickly. And see what happens. If you ask conceptually, why do you diversify? whatever the criteria might be, expected utility, maximum, minimax regret, it's that there are errors you can make. Maybe treatment A is better than treatment B, but you get it wrong and you put people in treatment B. Then you'll make an error. But you can have the error, that's a type 1 error, say. Or you can have a type 2 error that maybe B is better than A, but you put people in A. Well, if you put everybody in one extreme, do a singleton allocation, that everyone gets A or everyone gets B, then maybe you're lucky and you make no errors at all, or maybe you're unlucky and you get a very large error. If you diversify, then what you do is you will make both kinds of errors because you're putting some people in one treatment and some in the other, but you will reduce the potential magnitudes of the errors. You can see this starts to be congenial to minimax regret because you talk about how big an error can you make that's relative to an optimum. And what minimax regret is aiming to do in terms of the formal structure is to minimize the sort of maximum error, okay, as things go on. So that's what's going to happen. And it's going to turn out, as we'll see, that minimax regret is going to lead you to, when you have two treatments, to always diversify. Okay, and that was a kind of new result back 15 years ago. I've just talked that through. Now let's just go through that with a little tiny bit of math. Simplest case, one period problem, individualistic treatment, linear welfare. Individualistic treatment means there's no social interactions. What the outcome for a person who gets one treatment, fine. That's what they get. There's no interaction with what else happens to someone else. For general medical clinical problems, it's perfectly sensible. For lots of economic applications and labor market programs and so on, it's perfectly sensible. A case where that assumption would not hold would be something like vaccination against infection disease, because then there are obviously interactions. If I get sick, I may infect someone else. But let's make that assumption here. So you have a population called capital J of observationally identical people. They have, this is kind of standard notation in literature, is YJ dot is the outcomes that map treatment into outcomes, YJ of T. There's a population distribution of treatment response. Very important that we want to allow for heterogeneity in treatment response. The early literature tended to assume that everyone would respond to treatment in the same way. It was called constant treatment response. That's a very unrealistic assumption. It has very strong identifying power, but it's very unrealistic. So that's hardly ever done today. And you want to allocate people to treatments A and B. And what can you do? You can either put everyone in treatment A or everyone in treatment B, but more generally here, you can choose a fraction delta in the 0-1 interval that randomly assigns a fraction delta to treatment B and 1 minus delta to treatment A. Okay? So that's your problem. Now, we'll assume, to make it concrete, we'll assume a utilitarian planner wants to maximize mean personal welfare. So now we're going to have a personal utility function, UJT, which is what personal utility is as a function of the outcome that I get from treatment and of the treatment. So it's just a little more abstract than just a Y. It's just U as a function of Y. But it's just the utility of giving someone that particular treatment. And because we want to have a social welfare function, we're going to have these utilities be cardinal and interpersonally comparable, because we're going to go like Jeremy Bentham and we're going to add up utilities across the population. Okay? As a technical device, instead of adding up utilities across the population, we're going to compute average utility across the population, a mean utility. It just simplifies the math a tiny bit. And so now we have, if this alpha is the expected value of UA, is if everyone were to get treatment A, then the mean outcome in the population would be the expected value of UA, and so for short, we'll just call that alpha. If everyone would get treatment B, then the mean of that is expected value UB, we'll call that beta. And so now we have our, this is our ideal, this is our welfare function. Social welfare function is mean welfare with allocation delta. It's going to be W of delta. This is like before I have states of nature. This is talking about the truth, okay? Then we'll get to the states of nature. And so what the social welfare with allocation delta is going to be this right here. In words, some fraction delta are going to get treatment B, and then their average welfare is going to be beta. And then some fraction is going to get treatment A, that's 1 minus delta, and their mean welfare is going to be alpha. So this is my social welfare with allocation delta, and then I can rewrite that here as alpha plus beta minus alpha delta, okay? Now, this is this is not undergraduate level. I think I could, I don't think I could give it to my 10-year-old grandson yet, but hopefully in a couple of years I could, and say, what should I do? Well, you look at this, obviously, you get to choose delta, and if beta is greater than alpha, then the best thing is to make delta equal to 1. If beta is less than alpha, you want to make delta equal to 0. If beta is equal to alpha, you don't care. You're indifferent. So that's what I write here. And so the optimal treatment choice is this. You make delta equal to 1 if beta is at least equal to alpha, delta equals 0 if beta is less than or equal to alpha. Beta minus alpha is the average treatment effect. For those of you who've studied program evaluation and you want to learn the average treatment effect, that's the centerpiece of empirical analysis. That's what I said before. So if the average treatment effect is positive, you want to do one thing. If it's negative, you want to do another thing. Ambiguity comes in if you don't know, if you have partial knowledge of alpha and beta, and particularly don't know the sign whether beta minus alpha is positive or negative. Okay, so that's when the analysis begins. Now we get back to our states of nature. And, for technicality, I want to run over this quickly. I'm going to assume that the possibilities for alpha and beta are lying in some bounded set, okay? Because that's just going to matter for technical reasons. And then ask first, what would a Bayesian do? Well, the Bayesian, that's maximizing subjective expected welfare, just puts a subjective probability distribution down on the alpha and beta, computes subjective expected utility, which is this, and maximizes that. And so what the Bayesian then does is it will do the singleton thing. It will put everyone in B or everyone in A, depending on whether the subjective mean is higher or lower. This is a risk-neutral Bayesian. Okay. Maximin, here's the problem you solve, is if, say, in each possible value of delta, each possible allocation, what's the worst that could happen to me is the minimum of alpha S plus beta S minus alpha S delta. That's my welfare in state of nature S across all states, so that's my minimum. I maximize the minimum. Crank that out, you get your maximum solution. Now, in general, that depends on the topology of the state space. It can get to be a complex problem. If it's an issue where the state space is rectangular, so the minimum possible value of alpha and the minimum possible value of beta are both compatible, then this thing becomes very, very simple. And you just look at the worst possible value of alpha and beta and go with it. You do not diversify in that case. Minimax regret is down here. This is formally what I said. This is our in state of nature S. This is the best that you could do if you knew the truth, is the maximum of alpha S and beta S. If I choose some delta between 0 and 1, this is what I get. The difference between those two is regret. Maximize that over the states of nature. That's maximum regret, and then choose the value of delta that minimizes that. So now we have a problem that my 10-year-old grandson cannot solve, but it's one that any undergraduate at Cambridge should be able to solve. This looks a little complicated because there's a min and a max and another max, but if you just parse this problem, it actually turns out to have a quite simple analytical solution, okay? I can't say you should put this on exam because it's already in my textbook with the solution, so that would be cheating. But you could, if you want, you could try to do it on your own. And without going through all the details of the math for the lack of time, let me just say that if you solve the minimax regret problem, and the basics are down here, and then you have to work out the intermediate steps, the minimax regret solution is a fraction. It's this thing MB, which is defined up here, but that's computable, divided by the sum of MA plus MB, which is also computable, and that always lies strictly in between 0 and 1. And so you get this basic result that with minimax regret, you will always diversify. And by the way, this can apply to portfolio and allocation in finance too. You might ask about a financial investor who doesn't have a probability distribution on the returns to stocks and bonds and decides to approach portfolio allocation from a min-max regret rule. Then the investor will always diversify his portfolio. Okay? So I have there's a caveat here, a note. The math on this that I said could be solved by any undergraduate if you work at it with 2 treatments is very simple. Once you have 3 treatments, so you have treatments A, B, C rather than A, B, this is a very hard problem. I reference here Stoyer, 2007. That's Jörg Stoyer. He was a PhD student of mine at Northwestern. He's a full professor, econometric theorist at Cornell University now. Back when he was a student, he looked at the situation with 3. And the mathematics changes drastically with 3 treatments rather than 2. There are reasons for it. I don't have the time to go into them in terms of why it's a harder problem. The only thing I'll say for those of you with a math background, there are problems that are very easy on the real line that can become qualitatively more difficult in R2, 2 or 3, any higher dimensional space. Here we have 2 treatments, but the problem is really on the real line because you really care about just about the differences in outcomes across treatments. And so this becomes a fully ordered problem with 2 treatments. Once you have 3 treatments, this goes into R2 and you get semi-orderings. And it's, I'm mentioning this to you if you have a math background, that even Jörg's work was published more than 15 years ago. There's really not much more that's known about this since then. So there is some kind of, if there's any, I'm not saying it requires Isaac Newton, but it does require, some proficiency in math to do this with 3 treatments or more. So I'll just mention that. Okay, so that's the basic result. Then I go on, and I just want to generalize this in a couple of ways. The welfare function that I mentioned was just alpha plus beta minus alpha delta. Well, you may take some monotone function of it. This is what goes on with risk aversion in the economics literature, where you say my utility is not money, it's some monotone concave function of money. And so then you can ask the same question, what will happen with different functions f, okay? Now, what everybody knows is that if you're Bayes, if you're maximizing subjective expected welfare, if f is convex, then you're so-called risk-loving, then you're not going to diversify. But if you have concave segments, so you're risk-averse, at least in some regions, then you may diversify. And this is standard analysis of risk aversion in finance. But now let's look at maximin and minimax regret. And this becomes interesting. It turns out that if I put a function f on this, then the maximin solution does not change at all. It doesn't matter any monotone increasing function f. The maximin solution is exactly the same. If you look at the math of the maximin criterion, all that matters is the ordering of welfares. It's entirely ordinal. And since this function f is just taking an ordinal transformation of the original thing, it just doesn't affect the result at all. In that sense, it shows you maximin is fundamentally different than maximizing expected utility, where we need to have cardinal welfare, cardinal utility. Maximin is just only based on ordinal utility. Well, what about minimax regret? Maximum regret, you go back to having cardinality. In that sense, it's like expected utility, because you're taking the difference between the optimum and what you get with any action. That makes the problem cardinal again. But if you do out the math, so the function f does matter, but what I prove in this 2009 paper is that as long as f is continuous and there's ambiguity, then the minimax regret allocation is still fractional. You still diversify. The fraction you put into each treatment changes, but it's always diversifying. Mostly, in general, you have to do a numerical solution. If f is particularly the log function, then it's easy to solve analytically, and you get this fraction, which is different than the one that I had before. Okay? Now, the final thing I want to mention on this, and then I'll turn briefly in the remaining time to the tuberculosis case, because I don't have that really much time to get into it, is to move away from utilitarianism. when I first did this, and I'm sure this comes to your mind as well, if you start talking about diversified portfolios in finance, well, fine. You're the investor. It's your money. Do whatever you want with the money. If you want to put 600 pounds in stocks and 400 in bonds, then do whatever you want. If you talk about social planning, you're talking about observationally identical treatment of people. And now we're going to put 600 people in treatment A and 400 people in treatment B. And then you say from an ethical perspective, but wait a minute, this violates an ethical principle of equal treatment of equals. And you say, well, maybe I don't want to be utilitarian. The utilitarian solution was to diversify if you're doing min-max regret. But then you start to worry and say, maybe I don't want to be utilitarian. So I spent a lot of time fussing about this issue. First point to make is that what I did talk about with diversification is consistent with equal treatment of equals in one sense, but not in another sense. It's 100% consistent with equal treatment of equals in an ex-ante sense, because if I say there's probability 0.6 you're going to get treatment A and 0.4 that's going to get treatment B, then everyone has the same probabilities, 0.6 and 0.4. So ex-ante, you're all being treated equally. Where you get a violation of equal treatment of equals is ex post. That, of course, you flip the coins, and 6/10 of the people get treatment A and 4/10 get treatment B, and so ex post is the difference. So if you're worried about equal treatment of equals, it's about ex post equal treatment of equals, not ex ante. Now, so can society tolerate that? Well, there is an area in which society routinely tolerates that, and that's exactly in running randomized experiments. Because in running randomized experiments, you get equal treatment of equal ex ante. Everyone has the same chance of getting randomized into one treatment or another. But then the coins get flipped, and some people get treatment A and some people get treatment B. So we accept that routinely with randomized experiments. The issue here from the ethical perspective is that although not always, but typically we require informed consent when we're doing randomized experiments. So you say, well, people agree to be randomized, so okay, it's ethically okay. They don't always get informed consent. There are some classes of experiments where people are randomized without informed consent, and then it's precisely the issue. So if you say, well, this is crazy, I can't go with this ethically. No, there are certainly cases where we do exactly this. Okay, but what I did in the paper is to go beyond that and say, well, say you really are concerned with ex post equal treatment of equals, then what am I going to do? Well, then I move away from utilitarian social welfare function and say that there's some social cost to moving away from the extremes of a 0 or a 1. And mathematically, I just pose that as a fixed cost that gets subtracted off of social welfare if you move away from the extremes, and then you can resolve the problems. So that's what I do, analytically in the paper, is you resolve it, and then redo particularly the min-max regret analysis. Not surprisingly, the result is that if you care about deviation from equal treatment of equals, but not that much, if the fixed cost that you have to subtract isn't that great, then you continue to diversify. And it doesn't change at all, because with this fixed cost, it doesn't matter how much you diversify. That's the way the fixed cost is set up. But if the fixed cost gets large enough, then you say, I'm not going to do that, and I'm just going to do a 0-1 solution. Beyond this specific application, the main point to be made is that if you want to move away from utilitarianism towards a social welfare function, we want to express ideas of fairness or equity, you can do that. But you need to be formal and say, what do I mean by fairness or equity? Yesterday I talked about the medical work on race and risk assessment, how there's a lot of talk about fairness and equity, but they don't formalize what they mean by fairness and equity. What I think, and my co-authors on that paper think, is if you want to embed fairness and equity notions in social planning, then you should need to be explicit about what you're doing. Okay? Okay. I've got one more thing here that I'm going to skip about adaptive diversification for lack of time, and let me just, in the remaining, I have about 15 minutes, talk through briefly the application to tuberculosis and what Rachel and I did, and then, of course, we can talk about anything in the Q&A time after that. So this paper was in the Proceedings of the National Academy of Sciences, 2019. TB is still an important problem in the world. The statistic in 2017, 1.6 million people were certified to die from tuberculosis. Treating tuberculosis is actually not a difficult problem these days. The pretty well accepted treatment is a certain course of antibiotics. But it's not like taking penicillin for a few days for strep throat. It's a much more severe course of antibiotics, but it basically works. And so treatment is not a particular issue. The major issue with TB has been diagnosis of, and this is where the ambiguity is going to come, is diagnosis of tuberculosis. And there is a what a medical person would call the gold standard test for diagnosing TB. It's to take a culture or something and let the culture grow. The problem is that it takes several weeks to grow the culture, and you can't wait for several weeks to treat the patient. We're talking in a context of sub-Saharan Africa. People are out in villages. They may be hard for them to come into clinics. They come into a clinic and they want to get diagnosed and then go home and hopefully get better. But you can't wait. People may die if you wait 3 weeks for the culture to grow. So there has been a kind of standard test that's called smear microscopy, and it has well-known properties of accuracy, what are called sensitivity and specificity in the medical literature, and you can get a result pretty much right away. You don't have to wait 3 weeks, but it's not that great a test. So you'll be maybe making errors, type 1, type 2 errors, in treating people who don't need to be treated based on the result of that test, or vice versa. A new test was developed called the Expert, nice name. It was endorsed by the World Health Organization in 2010, and it also gives a very fast result, and presumed to be a better result in general, better specificity and sensitivity, but not entirely clear. There's some ambiguity about exactly how good the test is, but it's, there's been enough testing to know it's better than smear microscopy, and it's expensive. It requires a lot of equipment in the clinic, okay? So you can't just say, well, let's give everyone that diagnostic test now. It's a real decision that the public health clinics have to make. After Expert came in, it was agreed that it was going to be a better diagnosis, but then they actually randomized people into getting that test versus the older test, and then they looked at outpatient outcomes and morbidity and mortality, and the public health researchers found that it wasn't helping, that patients weren't any better off, and so there was this mystery. Okay, that's where Rachel and I came in. We couldn't really solve the mystery, but we decided to try to think through the whole decision theoretic problem and formalize the decision theoretic problem of a two-stage decision problem. It's not just a problem of choosing treatment A versus treatment B. It's a two-stage problem of first deciding, do I do this test or not? And if I don't do the test, then I treat the patient right away, okay? If I do the test, then I wait for the result, which I get pretty soon, and the test has a binary outcome. It's either positive or negative, as a typical medical test is, and then I make the treatment decision after observing the test result, okay? So for any of you who have had any most slight familiarity with decision trees and optimal control, this is a very simple two-stage decision tree. First decide whether to test or not test, and then if you don't test, treat. If you do test, wait for the result, and then treat. In order to solve that as an optimization problem, you do that by backwards induction, as typically with a decision tree problem of this time, and you're okay. The problem is going to be that you can't solve the optimization problem because there's stuff that's unknown. In this what we go through in the paper is we write down a very explicit version of the two-stage optimization problem and say what would be the optimal things to do with given background situations, and it will depend on patient covariates on what you know about the patient, because they're not all observationally identical. The patients come in with different medical histories. Some have fevers, some don't. Some are coughing, some aren't. They do chest x-rays as a very crude test, and they get different results on the chest x-rays. And you might do various things with the different patients. But you could do that optimally. We go through that whole optimization, but then we say, but look, you really can't solve that optimization problem because there's too much that's unknown, okay? So one thing that's unknown is we don't have full information about the accuracy of the test. That's what I said before. Then I mentioned before that treating TB is pretty easy. We know it's going to be antibiotic versus not, but that doesn't mean we know when someone should get the antibiotic or not, because we don't know whether they have TB or not. The big uncertainty problem for the medical doctor is that you have to make the decision on whether to treat or not before you have, without complete knowledge of whether the person has TB or not. All you're going to have at most is a probability of getting TB, and you can make that decision based on that probability. Now, we go through all this in the paper. This is like the medical risk assessment problem. It's exactly the same as what I was talking about yesterday when talking about using race in medical risk assessment. We have a probability of having TB, given what you know about the patient, which may or may not include these test results, depending on whether you do the test or not. Now, but I said that there's going to be ambiguity. We're not going to have, the doctors are not going to have rational expectations. Very important reason why the doctors are not going to have rational expectations is that even if you do randomized trials and actually get good results on the probabilities of illness for different kinds of patients, if you look at the medical literature, and I'm going to talk about this in TB context, but this is a very broad point, probably the most important that I want to make in terms of a source of ambiguity in a whole class of problems, is that the medical research literature reports results on medical risk assessment not conditional on all the covariates that a doctor would actually observe. So a doctor in the field in sub-Saharan Africa, we actually do some analysis in South Africa, in Cape Town. They're going to know lots of things about the patient. They're going to know age and gender and health histories and the results of their x-rays and on and on and on. There may be a long vector of things that the doctor will actually know about a particular patient. If they go to the medical literature and you find some prediction, it may be a logit model of whether someone has tuberculosis, or it may be called a machine learning model. It just depends on what language they use. It will give you a probability of having tuberculosis conditional only on a small subset of the covariates. But then the doctor knows a lot more, and the doctor won't be able to use all the information that they have to get the right condition, to personalize the treatment. In medicine, you want to have personalized treatment that conditions on all the information you have about each patient. You're not going to be able to do that. And that for tuberculosis, and we document this in some length in the TB context in terms of what information is available in terms of risk assessment of tuberculosis, is you're not going to be able to condition on everything the doctor wants to. And so there's going to be ambiguity there. Well, we set that up. I'm not going to go through the slides at all. I'm just going to talk it through in a couple of minutes and then end. We talk all that through, and we have this multi-stage decision problem. What you'd like to do is to solve the minimax regret problem, we say, where this is more complicated than just treatment A versus treatment B. It's actually, should I test or not test? And then if I choose a not to, that could be fractional. I might test some fraction of people and not test others. And then if I don't test, then do I choose treatment A or B? That could be fractional as well. And then if I do test, I may get a positive outcome of the test, and then it'll be, again, what fraction of people get treatment B versus A? And then if I get a negative result, again, what fraction will get treatment A versus B? It turns out there are 4 deltas. There are 4 of these fractions that a doctor should jointly choose in order to solve the minimax regret problem. Even in this case, that was a hard problem. And we didn't, I mean, I could brute force computationally, go in and try to solve the minimax regret problem with those, choosing those 4 fractions. We wanted to have a simple result that a public health agency might possibly use. And so we did something which you might call second best for computational tractability, which is to, instead of looking at it as one problem of choosing 4 deltas, we look at it as a kind of what we call a piecemeal welfare economic problem, where we view it as 4 problems of choosing, which is each binary choosing each of the deltas, and apply the minimax regret criterion into each one separately. This is not the global minimax regret solution that you want. It's a simple tractable thing that we did to make the results hopefully understandable and usable. But we thought, this could actually be used in practice. And then we go on and do some application in Cape Town, South Africa, and that's that, okay? So I'm really kind of sorry you don't have time to dig into this or any of the other, particular kinds of applications, but I at least wanted to give a flavor of it. This is not just theorizing that, you go in and deal with specific problems and see what you can do. And you've got lots and lots of references in the both from the slides or in that working paper I mentioned yesterday on credible social planning and uncertainty. So if you're interested in, there's plenty of stuff to dig into. Okay, so with that, we'll stop the formal stuff to keep on time. And